Good evening, good evening. Hope everybody's doing great, doing all right. All right, think everybody's in. If we don't be 100% in. Oh yeah, most definitely cool with that. Hope you feel better soon. Most definitely. All right, so I guess we'll go ahead and get rolling. And then if anybody have any questions or anything, we'll address those, before we close out. So let's see. All right, so we left off, we did 5-1 last class. So we're looking at 5-2 today. Finding theoretical probabilities. So we're getting into probabilities. So first thing we discussed is an experiment. It's just any process with uncertain results that can be repeated. So example of that is flipping a coin. And the sample space is going to be all possible outcomes of an experiment. So is that as far as flipping a coin goes, heads and tails would be the sample space, all possible outcomes of flipping that coin. All right, scrolling up a little. An event is going to be any collection of outcomes in the sample space. So for this example, if we say what's the probability of landing tails face up, then tails would be the event. If we ask about the probability of landing heads, then heads would have been the event. All right, everybody done with experiment? Oh, somebody trying to come in. There we go. So complement is going to be all outcomes in the sample space that's not the event. So if you were looking at the probability of landing tails, then the complement would be everything else. In this case, landing heads would be the complement. All right, so the notation for the complement is going to be whatever you call in that event, and then like a superscript C, like an exponent. So if I name my event E, then what represents the complement of E is E with this C, superscript. So if I name my event A, then A with that C superscript will be the complement of A. So. All right, everybody okay? Anybody still holding on to complement? All right, so when it comes to probability, we have two rules that they give us initially. I don't want to scroll up too fast though. Somebody else coming in. All right, so the first rule is that your probability is always going to be between 0 and 1. There can be a 0. Notice it has the bar under that, under our less than sign, so it can be 0 and it can be 1. 0 represent 100%. I mean, 0 represents 0% chance. 1 would represent 100% chance. All right. So that's the first rule. No such thing as a negative probability, and it can't be greater than 1. Then the relationship between the complement and your regular event. If you have the complement, the probability of your complement, and you want to know the probability of your actual event, you can subtract it from 1. Or if you have the probability of your event and you want to know the complement, subtract that from 1. Or basically the bottom line is that both of your probabilities, the probability of your event and the probability of everything else, we add those together, it'll give you 1. So all of these are the same rule, just manipulated according to what you want to find. All right, gonna scroll up some. And this is just putting into words what the symbols mean. The probability of the complement is 1 minus the probability of the event.
So A is the event?
Yes, in this case, A would be the event. Yep.
Mm-hmm. Okay, but it can be whatever letter. It doesn't
mm-hmm.
always.
Mm-hmm.
Okay.
Yep. Yep. All right. Let me know if I can't scroll up. All right. Rule 3, the way we will calculate our probability is we'll take the number of outcomes in A and place it over the number of outcomes in the sample space. So remember, the number of outcomes in your sample space are all of the possible outcomes. So you place that over the number of outcomes in the sample space. Done with the black. All right, so let's go back to flipping that coin. So let's do a light example. If I want to know the probability of landing tails, it's always good whenever you're trying to find a probability to go ahead and establish your sample space. We already did that for this problem, but just rewriting it so we can see the process. So our sample space is heads and tails. Remember, your sample space is all of the possible outcomes that is in that experiment. It almost look like a U. So all the possible outcomes in that experiment, so heads and tails. So the number of outcomes in the experiment is 2, just these 2 events. Now our event is landing tails. So I'm gonna call my event E. That was just me labeling it there. And so how many outcomes is in the event? It's just 1, and that's tails. So to find the probability, I would take the number of outcomes in my event, which is 1, place it over the number of outcomes in my sample space, which is 2. And if we were to convert it to a decimal, I believe you all know that's 50% chance of landing tails versus heads. Leaving it as a fraction is fine when you're dealing with, what my math lab wants from you. So you could have left it at 1/2. That's the foundation of finding your probability. All right, can I scroll up? You know, if I go too far.
Can you scroll back up a little bit?
Yep, sure can. Is that good? Or how much more you need?
A little bit more. Oh, right there. I'm right there. Yeah. I'm at
Okay.
the, yeah. Okay.
Okay. Yep, I'll wait for you. Not a big deal. Y'all know we got all the way till 9 o'clock.
I'm not trying to keep us there that long. I like the replay option.
I came in late. We in class till 9 o'clock tonight.
I don't want to be recorded
No.
saying what I really feel, so because y'all want a recording of this, so I don't want to say what I really feel. So I'm gonna just go ahead and just keep looking at my phone while she copy. All right, are we good with scrolling up some? Okay.
Yeah. Sorry.
Oh no, you're fine. You're fine. No big deal. Just let me know if I need to stop anywhere or see if I can get this whole question. Yeah, that's the whole question. All right, so next example, 10 dice in a bowl. So we reach into a bowl that contains 5 red dice, 3 green dice, and 2 white dice. What is the probability of picking a red die, then B, green die, C, white die? All right, scrolling up some. So we want to see the probability of rolling a red die. So remember, the first thing we want to do whenever dealing with probability is to establish our sample space. So we have 5 red dice, 3 green dice, 2 white dice. So we can go ahead and add those together. And we have 10 dice all together. That's the number of our sample space. 10 dice to choose from. Now, as far as red dice, we only have 5. That's our event. So the probability of getting a red die is 5 out of 10 chance, which reduces down to 1/2. All right, everybody good? Everybody okay? Next one, green die. So we already know the sample space is 10. We've already established that. We don't have to redo it. You know, we're in the same problem, so it's 10. And there are 3 green die, 3 green dice. It's only die when he's picking out one, right? 3 green dice, and that's 3 over 10. Any problems? Any problems?
I have a question.
Yes.
So the S in the beginning of A and B, the in quotations S, what does that stand for again?
The sample space.
Sample space. Thank you.
Yes, no problem. And I remember somebody in the class that mentioned, can your letters or can your probability use any letter for your event? That is the one letter that I would say is off limits, is the S, because normally the S is reserved for your sample space. Sample space represents all of the possible outcomes. So that's the only letter I would suggest not using, since S is already designated for your sample space. Yeah. Any questions? Any questions? Last one. White die. There are two of them. So that's 2/10, which reduces to 1/5.
Space is 10. Mhm. Okay.
All right. Any questions so far? All right. Holding up some. Anybody holding on to the green? All right. So the next one, we have two dice. We're going to roll two dice and add the outcomes. What is the probability that the sum of the two dice is 7? All right, we good to scroll up? Make sure we good. Okay, so just like before, we need to establish our sample space. Now here is a little different than just counting off, because we have two dice that we want to give an account for. We want to give an account for all of the possible outcomes that two dice can present. So you're talking about, when you look at it right here, I'm talking about when die 1 is 1, die 2 is 1, die 1 is 1, die 2 is 2, 1, 3, 1, 4, 1, 5, and so on. And remember, each die has 6 faces. Ever played Monopoly before, or any type of game board game, you have 6 faces in total. So you also want to look at all the possible outcomes when die 1 is 2, and then go through the list for die 2. Die 1 is 3, all those outcomes. So what you can do is use the fundamental counting principle, which is right here, and says that if you have 6 options or 6 faces for die 1, 6 faces for die 2, you can just multiply them together, and that will give you the number of all possible outcomes that will be created. So in other words, let's say if one die had 6 faces and the other one had 8 faces, then it would be 6 times 8. Or if one had 10 and one had 9, 6 times 9. You have some weird dice going on, but that's what you always can do, is multiply your options together, and that'll let you know the number of all possible outcomes. All right, everybody good before we go to the next part? All right, everybody good on the black? Scrolling up. All right, so we want to know how many different ways can you add the two numbers up and get 7? So we will look at all of those possibilities. So our event is roll of 7. And here we go. We're talking about when die 1 is 1, die 2 is 6, die 1 is 2, Die 2 is 5, 3, 4. And then 3, 4, and 4, 3 are different outcomes because 3 is die 1, 4 is die 2. But die 1 is 4, and then die 2 is 3. Like I said, it's different outcomes. Then you have 5, 2, and 6, 1. So we have 6 possible ways that we can get 7 by rolling these 2 dice. All right. So once you have that, that's 6 over 36. That reduces to 1 over 6. All right, scrolling up, pretty good. How far are we up here? Anybody holding on to the black? All right. So this chart right here represents the education and marital status for 665 randomly selected US residents. So let me erase this. Why is this not erasing? There we go. Anybody need to read? All right. So education level is that first column. So you got less high school, college or higher. Then total. Then across the top, we're looking at single, married, divorced, widowed, and then total. And then we see our numbers 17, 68, 27, 112, 70, 240, 98, 408, 10, 59, 15, 84, 28, 30, 361. Then final column 125, 397, 143, and 665. All right, can I scroll up? So suppose we select at random from the collection of 665 people. What is the probability that the person is married? All right, scrolling up. So total number of people that we have is 665. That's our sample space. And then if you're talking about total number of people that are married, that's the only characteristic we have. So that's what we're looking for. Total number of people that are married is 408. So we take that 408, place it over the 665.614. So everybody done with the chart? Everybody still copying the chart? So we good? Okay. So 61.4%. And just giving you the 3 different ways you could represent the answer. MathLab will let you know how they want the answer. But yeah, either way, that's the answer. All right, we're good at scrolling up. All right, next one. What is the probability that the person has college education or higher? Has a college education or higher? So if you go back to the chart, college education or higher, these people right here, 143. So that's why we did 143 over 665. All right. Are we good? Scrolling to see. So here it says, what's the probability that a person is married and has a college education? So this time we have two characteristics we have to give an account for. So give you a chance to write that down and we'll go back and look at the chart, see what fits that category, what number of people fit that category. All right, so our probability, or our probability, our sample space is 665. That's still the same. Now we're looking at the people that are married and has a college education or higher. So going back here, here's our married column. Here's our college education or higher for column. So that meets right here at 98. Those are the people. Somebody
That
got to-
Okay, got it.
that are married and have a college education.
Yeah.
So that's 98 over 665. So just a statement about the word and that consists of only those outcomes that are in both events or that are both events. So that was the one, the total number of people that had both. You know, so and is always what they have in common.
We said 98 divided by okay. Got it.
All right, can we scroll up?
The word inconsistent.
Like holding on to the red, don't want to go too high. Okay, so then you may see the word or. Let me see, do we have or? Oh, that's the next one. Okay, so the word or consists of all outcomes that are only in A, that are only in B, or in both.
I see you over there. Good.
All right, scrolling up. Anybody need the purple? All right, so here we're looking at what's the probability that a person is single or married. Let me see, why did I do this Venn diagram? Hold on 1 second, y'all. Okay, I just probably use it to explain. Okay. What's the probability that a person is single or married? All right. Who's holding on to the green? Green, green, green. Okay. So what's the probability that a person is single or married? So they gave you a Venn diagram just to give you an idea as to how this thing works. So you let circle A represent event A, circle B represent event B. So when you talk about the part that they have in common, the and, that would be that red shading. That's what's in common with both. Or is going to be the green, red, and purple added together. That's all of each circle. All right. So if they ask you about Venn diagram, you need a visual. That's how that normally works. Once again, that 98 would have been what the red would represent. And then what we're about to find now will represent, be represented by all three pieces. You add up all the pieces together. All right. Give you guys a chance. All right, so let's see how this works for us in the chart. So we want single or married. So let's go up and see what pieces we need. I know you guys got it right in front of you, but I got to scroll up. So our single people right here, married people right here. So you're talking single or married, we should be adding up those columns. All right. And so let's go down here to it. Now, so that total, and I didn't even look to point out the total. So our total is what we'll be adding up. Now, we have another one, I think. Let's see if they ask for it. Hold on. Then we're gonna ask for the pieces.
So the N sample space.
Okay.
And this
I can't
will
hear
be
you say it again.
665.
Say that one more time.
So the sample space would be still equal to 665.
Yeah, because we're in the same problem. Yeah, we haven't changed problem, so we're still using the same chart. So our bottom number is still 665. So we're looking at our total number of married folk and our total number of single folk. Now, they don't have anything in common, so we could just take these two pieces. Somebody said something in the chat. Oh, no. Okay. All right. Yeah, no problem. Not a problem at all. So we can just take our totals. You'll see in the next example, we have to look at each piece, and I'll show you why in a second. But because there's no such thing as being single and married at the same time, well, I guess unless you have an entanglement, right? We got a lot of stuff going on nowadays, right?
You know, they can do it.
Right.
They can juggle.
People making it happen nowadays. So back in the day, you were either single or married. Let's do it like that. So we can just use our two totals right here, 112 and 408. But you'll see in the next one when it's possible to have something in common. So you have to give an account for that, but we'll see in the next one. But yeah, so that's what we did here, 112 and 408. Add those together, they give us 520. Put the 520 over 665, and that'll give us that 78%.
Oh, okay. The 1 plus the 4. Okay. Got it.
All right, are we cool to go to the next one? So the next one, what is the probability that a person is married or has a college degree? Now here we have to be careful. Can't just take the totals because it is possible to be married and have a college degree. And so I'll show you why that's important in a second. Just want to make sure everybody got a chance to write that down before I scroll up.
I will get 78.2.
Mhm. All right, so the probability of being married, picking someone who is married or has a college degree. So now when I go here, and like I said, I know the chart is right in front of y'all. Y'all don't have to scroll up anywhere. But talking about being married, which is right here, then have a college degree or higher, which is right here. Notice if I were to just to take the 143 and this 408, these two totals, that would be great, but I would be counting 98 twice. So you have one or two ways you can do it. Either you can just add up your pieces, not the totals, just add up your pieces, which is what I did here. And I'm gonna go to the notes. That's what I did here, just added up the pieces. Or you can add up your totals, which is 408 and 143, and then subtract 98 from it. Because remember, if you're looking at those totals, you're counting you counted at 98 twice, because 98 is a part of this 143 and it's a part of this 408. So you just have to give an account for whenever you have something in common, to either not count it twice like we did here in this one, or subtract it after you added those totals together. So those are two ways you can get your event number. Once again, we're still in the same problem. So our total number of people altogether is 665. But those would be the two different ways you can get 453. Yes?
Can you just go over that one more time? I didn't catch it with the scrolling up and down.
You said like this? No, just playing.
Yeah. Add some strobe lights in there. We were doing good.
Not a problem. Let me erase some of this stuff so we can walk through it again. All right. So we're talking about the probability of getting someone, or the number of people that are married or have a college degree. So you're talking about this row right here and this column right here. So now in the last one that we had, we just added the totals because they didn't have anything in common. Like we said, by old school standards, you're either single or married. There's nothing in common. So there's not a problem there. You just add those two numbers together. But if I look at this column right here, this row and this column, you see that 98 is counted twice. There's
Mhm.
married people that's in that 98, and so the college people in 98. So I can't just take 408 and 143 without considering that 98 is counted twice. So what I said you can do, you have one or two options. Either you can just add the pieces together that makes up that row and that column, or you can add up the totals and then subtract 98 from it so that you're not counting 98 twice.
Okay, gotcha. That's easy enough.
Yeah. Okay, cool. And so that's, if I can get down to it, that's what this says right here. So just know that to get our event number, we have two options. Purple is adding them up together, all the pieces together. And then green is adding up the two totals and then subtracting what they had in common, which was at 98. Either way, we get 453. All right, scrolling up some to finish the problem. Then you take that 453, place it over 665, and that'll give you that 68%. All right, are we good? I think this is the last thing in this section. Anybody still copying? Let me know where to stop.
Excuse me.
Gotta go with the green. All right, so now we're looking at mutually exclusive events. We kind of mentioned it earlier. An example of that, these are events that do not have anything in common or any outcomes in common. So when we talk about being single and being married, those would be considered mutually exclusive events. So another way of looking at it is it is impossible for these events to happen at the same time. Everybody done with the top. Oh, so I wrote that right there in the green. The events of being single and married are mutually exclusive. All right, gotta scroll up some. So rule 4 actually leans into what we just finished doing with those two events that had that 98 in common. Notice what we did here. We take the probability of A plus the probability of B minus the probability of what's in common. And like I said, that's what we did with that 98. Subtracted the 98 from the addition of the two totals. And then, but if they're mutually exclusive events, like with the single and the married folk, we just add the probabilities together. So remember, there was nothing in common to subtract, so we didn't have to worry about that part. So those are the official formulas for what we just finished doing those last two examples.
After the word for, is that supposed to be amount?
Mutually, M-U-T, yep, I just mutually exclusive events.
Okay.
Yep. All right. Scrolling up. So we have roll a fair six-sided die. Find the probability that the die shows an even number or a number greater than 3. Oh, let me see. I think I want to change that to 2. Hold on. Do I want to do that? Greater than 3. Give me 1 second, guys. I think I want to do greater than 2 because both of those are 3/6. Yeah. I'm going to change that to greater than 2 just for a better visual. Yeah. Okay. Yeah. Let's roll a fair six-sided die. Find the probability that the die shows an even number or a number greater than 2. Let's do 2.
Yeah, the die shows a big number, number greater than 2.
All right. Everybody done with the black up there? So I'm gonna change these 3s to 2s as we progress through the notes. So just throwing that out there. So I'm gonna let E represent the event even number and let G represent greater than, I'll put it 3 strong. I'll put the 3 back there. Greater than 2. Right down to blue, just scrolling up. Okay, so let me erase some of the stuff. So the first one, we know the number of our sample space is 6. You have 6 possible outcomes. So if you're talking about the even numbers from 1 through 6, it's 2, 4, and 6. Total of numbers in our event is 3. And so the probability of getting an even number is 3/6. All right. Next one, roll in a number greater than 2. So that's going to be 3, 4, 5, 6.
Okay.
So it's 4 possible outcomes here. Excuse me. So that's going to be 4/6.
So with this being a 4/6, what would Math Lab ask for as the answer?
Oh, we're not finished yet. So when we look at our final answer, fraction, it'll probably ask you for the fraction. Yeah. But notice I didn't reduce either one of these because remember, we're going to add them, going back to those formulas.
That's
So
all.
yeah, so we'll reduce it at the end for our final answer. But right now we're going to leave it as is.
Okay.
And the reason being is if I reduce this, that's going to be 1/2. If I reduce this, it's going to be 2/3. But then when you have to add fractions, you're going to get your common denominator back again. So I'm going to end up changing them back to 3/6 and 4/6. So you might as well leave them as 3/6 and 4/6, and then we'll reduce at the end. All right, is everybody good? Can I scroll up to here? All right, so are the events mutually exclusive? That's MUT again. Try to shorthand it a little bit. Mutually exclusive. The answer is no, because they have 4 and 6 in common. So mutually exclusive means that they have nothing in common. So these events are not mutually exclusive. So that means we have to give an account for the 4 and 6, because when I look at this probability, it has 4 and 6 in it. When I look at this probability, it also has 4 and 6 in it. So if I were to add them together, I'm counting 4 and 6 twice. Also, if I were to add these together, I get 7/6, which is more than 1. And don't forget, our probabilities can't be more than 1 anyway. But the reason why it's more than 1 because we count 4 and 6 twice. So. All
Did
right,
you,
can I
you
s-
said mutually exclusive means they have nothing in common, correct?
Right.
Okay,
Mhm.
thank you.
Yep, not a problem. All right. Are you okay to scroll up? All right. So because they are not mutually exclusive, hold up, not mutually, right. Uh, right, okay. Had a brain freeze. All right, so once I got a lot of stuff going on now. Okay, so since they're not mutually exclusive, they have these two things in common. So we look at the probability of even and greater than 3. Even and greater than 3 would be 4 and 6. We already talked about that. So that means the probability of being even and greater than 3 would be 2 over 6. Those two outcomes of 4, 6 would be the 2, and we do 2 over 6.
Yeah.
All right. So there goes our formula. Go right down with the red. So we do the probability of our event E plus the probability of our event G. Try not to make my G look like a 6. It look a little better than that. So, and then the that's minus the probability of E and G. So that's 3 over 6 plus 4 over 6 minus 2 over 6. Somebody got a question?
No, I'm just looking at you, work it out.
All right. I'm gonna go back up. Just moving this out the way out off the notes. If I change that number. So add them together and subtract. 3, 4, 7 minus 2 would be 5 over 6. All right. Any problems? Can I scroll up?
And that whole problem,
Mm-hmm.
what is that called? What were we finding with the 5, 6?
Well, what's the probability of rolling an even number or a number greater than 2? So if you think about it, let's go here. Let's look at our numbers. So our even numbers, 2, 4, 6, and then number greater than 2. The other numbers that are taken up that aren't crossed is 3 and 5. So that's why it's not 6 over 6. The only one that's really not given a count for is the number 1. And so that's why it's a 5 out of 6 chance to roll a number that fits that category, either being even or greater than 2. And the only number that doesn't fit that category is the number 1. And so every problem you get, you won't be able to lay it out like that because these is dice. But yeah, that's what that means. Got a 5 out of 6 chance of getting a number even or greater than 2.
Oh, for some reason I thought that was for 3. Okay.
Oh, initially it was. I changed it and then I went changing it throughout the problem.
Oh, so even in the orange, it's supposed to say 3, or it's supposed to say 2 instead of 3. Because yeah, see where it says even and
Oh,
greater
yeah,
than 3. So that's
I
supposed to
missed
say.
that one. Yeah.
Oh, okay, okay. Okay, sorry.
Oh, no,
Got
wait, I'm
it.
sorry. You got me. I appreciate it.
I thought
mean,
I thought it was just a different like
uh-huh.
example. Okay.
Yeah, yeah. Yep,
Still on
thanks.
the same
Appreciate
thing.
it.
Got it. Thanks.
Appreciate it. Appreciate it. All right. Are they good with the orange?
Betty, did you check the dinner?
Nah, I didn't check for dinner yet. Um, so B, find the probability that the die shows an even number or number 5 on top. Everybody done with the black? All right. So this time we're looking for an even number or the number 5. So we know 5 is not even. So 5 wouldn't be included in that first category. So we talk about even numbers, which is 2, 4, and 6. So that gives us a probability of 3/6. And then just rolling in the number 5. It's only one number that fits that category, and that'll be 1/6.
I'm sorry, is that a by that 5?
Yep. Mm-hmm.
Thank you.
Mm-hmm. Not a problem. All right. Holding on to the blue. All right, so next move, just like before, are these events mutually exclusive? The answer is yes in this case, and that means they have no outcomes in common. No outcomes in common. And if they are mutually exclusive, this means we can just add the probabilities together. Don't have to worry about subtracting anything. All right, can we get up to the red? And we're still doing purple and black, purple and green. So since they're mutually exclusive, we can just add the probabilities together. 3/6 plus 1/6 equal to 4/6. And then we can reduce that to 2/3. That's yep. No, you're okay. Anybody holding on to black? All right, so we good? Okay. Hold on 1 second. Let me look at 5-3. I think 5-3 is that long. Yeah, 5. Yeah, we probably called up there. And we got that. Oh, okay, 5-4 is short. Okay, just looking to see what's going on with this stuff before we keep rolling on.
Are we gonna do all of that tonight?
Yeah.
Cause
Y'all
I'm like,
don't-
God, dog, my finger is cramping.
Yeah, so short.
Y'all don't want to, you know. I know somebody in here want to now. Don't trip.
Oh, no.
Somebody want to.
I can definitely, I can try. I can try.
I'll
So my
find a
hand can't
flaw.
do it no more.
Oh man.
That was funny.
My rotator cuff getting tired.
Your rotator.
Right. She
Man.
spoke what I was thinking. That
Yeah,
was
look,
funny.
Hey man, it's hard out.
I
It's
mean, but
hard out here
hey,
in these streets, man. It's
hey,
hard out here in
that's
these
what you got to
streets.
do.
People be, you know, saying, you know, I ain't doing no work around here, you know. So, you know, it's kind of tough, man. I don't know what to do.
I can't believe somebody would seriously complain about that and not even tell you about it. Like that was so ridiculous to me. My girlfriend and I were looking at each other in the car because we were both listening to it, and she was like, "Is somebody seriously complaining about that?"
Well, like I said, I'm in my other class, my 161 was, I mean, they were hitting me with the same thing. I was like, look, y'all don't know what to do. Like, I can't go back to the principal office I can't go 2 weeks in a row. Like, that was just last week. So it's like, you know, so I'm trying to stay out of the office, man. So trust me, I get it. I get it. Trust me, when I was doing 5-2, I was like, dang, I don't remember 5-2 being this long. I was sitting there, and I'm just talking through it. I was like, wow. That's why I said, man, let me see how long this rest of this stuff is.
Well, I think you're doing a fantastic job.
Thank you. I appreciate it. So maybe we'll at least do 5-3 since some of y'all hitting the canvas, y'all trying to tap out. So we'll at least do 5-3 and then go from there. All right.
Dinner too.
Look, I was trying to eat. 6:15 crept up on me real quick. I was like, man, but it's all good. So 5-3 associations and categorical variables. And so we're going to refer to that table that we just had in section 5-2 when we were talking about, you know, the married people and all the good stuff like that. So then, you know, I didn't think it was necessary to rewrite it. All right. So looking at conditional probabilities, it's a probability of an event that are affected. Probabilities, there you go. Probabilities of an event that are affected because another event has already occurred. So here, the notation that we have, they got probability A, got that /B. So that means the probability that event A occurs, given that B has already occurred. So that's the notation for that. All right, can we scroll up? All right, so the way we'll calculate the conditional probability, we want to find the probability of A given that B has already occurred. So we take the probability of A and B place it over the probability of B. Or if we have the numbers like we did in that chart, we'll take the number of A and B and place it over the number of B. So the positioning of your letters here, they do matter because B is the one that's going to go in your denominator. And so if you flip them, let's say if it was B/A, that means A would be down here in the denominator. So the position of your events do matter. All right, scrolling up. Very good. How far can we go? Let's go here. So suppose a person is chosen randomly from the chart. What is the probability a person has less than a high school degree is married? So the probability that the person has less than a high school degree is married. So in other words, the probability of, out of the people that have a less than high school degree, the ones you chose is married. So if we look at what that means as far as our probability is concerned, we're talking about the probability of getting someone that is married, given that less than high school degree was already chosen. So that's how we would, word that probability.
Go back down in the green a little bit.
Yep.
X, right there.
Mm-hmm.
I'm done.
All right. So if we look at the formula, the probability that someone you chosen was married, given that less than high school degree was chosen first. So notice the positioning of our letters. So up top is going to be the number of married and less than high school degree. And then on bottom will be the number of the less than high school degree, the total number of those. So that's going to be 70 over 125. I won't scroll all the way up. I don't want to mess anybody up. Mess some equilibrium up because they staring at the screen, right? But it's 70 over 125. If you go back to that chart, the 125 is the total number of total number of people who had less than a high school degree or diploma. And then 70 should be the category that has those who are married and less than high school. Mhm. Any problems with that?
So it's just 0.56, not 56%.
Same thing as 56%. Mm-hmm.
Oh, okay.
Mm-hmm. Yeah. And once again, MathLab will let you know which one they want.
Okay.
So just hold true to those directions. Everybody done with the blue. Don't copy that yet. I gotta see where it's going, but I don't want to mess anybody who's copying this part. So don't copy this yet. Trying to see what I was writing. Somebody might have asked me a question though. So it may just be some random notes. All right, can I scroll up? Everybody good? Oh, this is just me showing the probability. Okay, well, I mean, I guess we can talk about it. Hold on one second. Well, so here, so remember I told you when you go back to those notes, not notes, but go back here, you can either do probability or the number over the number. So you're not going to always have the number in the chart. And so if you have probabilities, so here, if you're looking at the probability of being married and have a less than high school degree, that's 70 over that. And my eraser is still on. Give me it back. There we go. So you have 70 over there, 665. Why is my stuff not? Sorry, y'all, my computer moving slow. Come on, let's go. Yep, you can do it. There we go. One more time. Here we go. Thank you. So the probability of getting someone married and have less than a high school diploma is the 70 over 665. Remember what we were doing last time? We would place over the 665 because that was our sample number, our bottom number. And then the probability of all of the people that were had less than a high school diploma was 125 over 665. So if that's what you would do if you were dealing with probability. So you take one probability, place it over the other probability. Then if you want to reduce it, this divisional bar is the same thing as this divisional sign. Only reason I did that is because don't forget, whenever you divide it by a fraction, you're going to multiply by the reciprocal. So that's what I did here. End up flipping the fraction. And my 665 can cancel out. And that'll leave me with that 70 over 125 again. So I end up getting the same thing. But if you had to do a probability over a probability, this would be the process. Everybody done with that top line? Anybody who's copying? And so you see, still we get 70 over 125, which is 0.56. All right, can we scroll up? So rule number 5, that's just what why would they do it anyway? Okay, so rule number 5 is what we just finished doing. And I want that to be black. So they just made it a rule. And then also they manipulated the rule. If you were to multiply PB to both sides, both of these are the same rule, just a manipulation of the same rule. So all right, everybody doing that top line. So next thing we're looking at are dependent events. Events that are associated are considered dependent events. In other words, they have a connection. Events that have conditional probabilities that change depending on different conditions. right, scrolling up, scrolling up. And so independent events, events that are not associated. The conditions of one event does not affect the probability of another. How's everybody doing? Dependent. Oh, somebody coming back in. Oh, yeah. There we go. So that in that red statement, if events A and B are independent, then the probability of A, given that B has occurred, is just going to be the probability of A. Because remember, if they're independent, then the probability of B has nothing to do with A, and it doesn't change A. So that's just a statement, one of those things that, my math lab may ask you as far as concept. So if your events are independent, that means one event has nothing to do with the other. The probability doesn't affect the other probability. The fact that B has occurred has nothing to do with A occurring. So that's why this is still going to be equal to the probability of A. All right. Scrolling up a little. If I go up too far, of course, let me know. So we have suppose maybe I need a new pen. I mean, a new battery for this pen. Suppose we have a standard 52 card deck. Are the events, the card is a diamond and the card is red independent. If you find another player holds a red card and you want to know if he has a diamond. Yeah, I read that wrong. I mean, I read it right. I just didn't read it with the right inflection. It's all right. I'm a mathematician. I'll be good. All right. So we got a 52 card deck and we want to know, are the events, a card is a diamond and the card is red independent. And then he says, if you find out, that should be 2 questions though. Do this right here. I don't know if the book wrote it like that or I just wrote it wrong, but so the card is a diamond and the card is red independent. Okay, if you find out another player holds a red card and you want to know. See something it must be something I left out of here. Was I looking right? I know this shouldn't be a question mark. Oh, the card is independent. If you find out another player holds a red card and you want to know if maybe it's, do you want to know if he has a diamond? Let's do it like that. Something is not right. I probably have to look it up in the book and see what it actually said, but I'm gonna write it like this. So are the events, the card is a diamond and the card is red independent. If you find out another player holds a red card, do you want to know if he has a diamond? Okay, let's just roll like that, see what happens. All right. Somewhere I didn't write, I missed a word or two from the book, but it's all good. Okay, so first question, are the events, the card is red and the card is a diamond, and the card is red, independent. So let me see. Did we talk about cards in here? Let's see. We never in this class we never established like house rules as far as cards or anything is concerned, right? I don't
No.
think- yeah, I didn't think so. Because some people may not play cards. You can't assume everybody's played cards. Hold on one second. Let me see if I wrote it down here. Okay, I must have took it to another class. Let me make sure. So before we do that, I just want to make sure everybody's clear. Has everybody written the blue at least? Want to make sure. Still see people writing, at least write the blue. And then I'm gonna go to the cards and make sure everybody's okay with cards.
The card a diamond and the card is red. It's an independent.
Mhm. All right, so can I go to the next page? Everybody good, good, good. All right, we're gonna come back to this, but I at least want to make sure everybody's good with these cards. Can't read this. Gotta be 5-1. Are you serious? All right, one last shot. I was trying to be lazy and I had to write this all over. I guess I'm gonna have to be late. Have to remove my lazy card.
Are you talking about
Hmm?
book 223?
Say that one more time now.
Talking about the question on page 223, dealing diamond?
No, I was just going to establish house rules as far as these cards are concerned. I'll just write it out. I was just trying to be lazy and not have to write it out. So, all right, because when dealing with this stuff, I can't ever assume that everybody's played cards or do play cards. So look at the standard 52 card deck.
What game we playing? Spades?
See, there you go. This is you one of the reasons we got to establish the house rules. I can tell that right now.
Teach us how to play poker, then we'll stay up all night learning how and winning money at the table.
see, y'all not right. And it's funny because these things right here, when you start looking at these in detail, this is the beginning of counting cards, of course, which is illegal, but I'm just saying that this is where it starts. These are foundational things. No jokers. So that's what it means by standard.
Jokers.
So there are 4 suits.
Diamond and hearts.
Don't want to go down one. Oh, shit. Yeah, I'm gonna go down one. Oh yeah, you can write this down. Well, it's up to you. I mean, if you're already cool with the inner workings of a 52 card deck, you don't have to write this down. But I can't assume that everybody is. So I got to make sure that everybody's on the same playing field. So
Thank you, because I don't play cards.
I know it had to be, it's gonna be at least one, at least one.
Well, I mean, I tried. I was invited to a game and then they were
Uh-huh.
like, get out of here.
Yeah. If you go to a real place to play cards, that's not the place to learn.
And did you
And
like
they,
that?
and they were my friends.
Yeah.
Did you like that?
Yeah. Look, we can be friends after the game. So
Right. That's exactly what they said. I was like, you gotta go.
oh, that is funny. So REG is just regular. I'm just gonna call them regular, even though ace is not really regular, but it'll be all right. Each suit. And I think that's it. And you card players, if I left anything out, let me know. But standard 52 card deck, no jokers. That's why it's called standard. So we have 4 suits. We have spades, clubs, hearts, diamonds, 2 black suits. In other words, all of their cards are black, considered black. So that's the spades and the clubs. Then 2 red suits. All their cards are considered red. That would be your hearts and diamonds. So 13 cards each suit. So you have 3 face cards, 10 regular cards. Your ace is not a face. And so we're talking about king, queen, and jack. And then your regular cards would be your ace, which can sometimes represent number 1, and then 2 through 10. So each suit has those 13 cards: king, queen, jack, ace, and 2 through 10. All right, we still copying. Anybody still need this before we go back to our problem? Everybody good? All right, let's go back to our notes. So get this out of here. Okay, so let's go back. We said suppose we have a standard 52 card deck. Are the events the card is a diamond and the card is red independent? If you find out another player holds a red card, do you want to know if he has a diamond? So like I said, I don't know if my wording was off, but we'll get to it. So let me see. Hold on. Got it. Okay. So we're leaning off of this thing right here. So what we're going to do is we're going to find the probability of A given B, and then find the probability of A. So if they match up, then these events are independent and it doesn't matter. So that's what we're going at. I still think I'm missing some words in here. Something didn't, translate all the way. But so let's look at the probability of A given B, and then we're gonna look at the probability of A. So the probability that a car is a diamond, given that it didn't say it's given though. See, something I ain't do right in this problem. But anyway, let's go through it. The probability of getting a diamond is 13 over 52. Matter of fact, I'm gonna leave this here. I'm gonna check that out later. Give myself a note. It won't stop us, but I need to check that out. So the probability of getting a diamond is 13 over 52 because it's 13 diamonds in the deck, 52 cards in the deck. And so that probability is 1 over 4. So before we go to the next piece, is everybody okay with that? The probability of getting a diamond is 1/4. All right, hold on 1 second. All right, now the probability of getting a diamond, given that the card is red. So found another way to hold a red card. You want to know if you have a diamond. So probability of getting a diamond, given that the card is red. So a card being diamond and red, of course, it's still a 13 out of 52 because all of my diamonds are red. But then the probability of red cards. So there are 26 red cards. Talking about the diamonds and the hearts. So there are 26 red cards. So that's why I have 26. Oh, give me my pen back. So that's why I have 26 over 52 right here.
Mm.
And remember when we did our probability cancellation and dividing out, that bottom number was the same. So we just canceled out. So I just shorthanded it this way, just went ahead and cancel it out. Because we know the 52 is going to cancel. When we spread it out, multiply by the reciprocal. So that will give me 13 over 26, which ends up giving me 1/2. I wrote the 26 red cards right here. All right.
So the
Hmm. So our events are not the same. You know, we got 1/4 and then we got 1/2 here. And so since the probabilities are not equal, the events are not independent. So remember, leaning back on this, I'm gonna scroll back down, but remember we said here, if these two are equal, that means our events are independent. So since they are not equal, that means our events are not independent. Got another conclusion down there. Let's scroll up. And so this means that knowing that someone has a red card is going to be useful in determining if that person has a diamond, which sounds like common sense, but this is the numerical rationale as to why it would matter. All right. All right, can I scroll up, scroll up? So this one, I think I wrote better. A card is face down. This time you want to know if your opponent has an ace. You discover he already has a diamond. Is this helpful? So this time we know that our opponent has a diamond. I mean, hasn't yet has a diamond. We want to know, is that helpful? Because we want to know if he has an ace, he or she has an ace. Anybody still holding on to the blue? So are the events independent? Is what we want to find out, just like last time. Are the events independent? So the first thing we can do is find the probability of getting an ace. Because we want to know what's the probability of getting an ace given that the person has a diamond. So we can just go ahead and find the probability of getting an ace straight up first. There are 4 aces in the 52 card deck. So 4 over 52 is 1 over 13 when you reduce. All right. So now we want to find the probability of getting an ace, given that you already know he has a diamond. So we're gonna look at the probability of an ace and a diamond over the probability of a diamond. So that top one, probability of ace and diamond. So how many aces that are diamonds? It's only one. So that's why that's a 1 over 52. And then the probability of diamonds, there are 13 diamonds in the deck. So that's 13 over 52. So cancel out that 52 and you're left with 1 over 13. All right. Since the probabilities are the same, the events are independent.
I was gonna say, I'm on that last part. Yep, right there. That's good.
Yep, not a problem. All right, can I scroll up now? All right, so conclusion here, this means that knowing someone has a diamond does not help you determine if they now have an ace. So because the probabilities were the same, that means the events are independent. So it doesn't help you. Yeah, we almost finished with this section, I think. All right, about done with the purple. for the first sentence. So this next rule, I believe it's the last rule. If A and B are independent, then the probability of A and B can be multiplied together. Well, if you want to find the probability of A and B, you can multiply them two together and get that probability. All right. So suppose that 51% of all babies born in the US are boys. What is the probability of a family planning on having 2 children will have 2 boys? All right, can we go up? So these events are independent. So, you're talking about boy versus girl. So these events are independent. Probability of getting a boy is 51%. 0.51 as the decimal. Let's scroll up. So now we're looking at getting the probability of a boy first and a boy second. And so just the probability of boy times the probability of boy. And it's 0.51 times 0.51, which is 0.2601 as a probability. Remember, we can do this because these events are independent of each other. Probability of having one has nothing to do with the probability of another having a boy. All right, so we got one more, but any problem with that? All right. What about a boy first and a girl second? So we already established that a boy is 51%, but then a girl is going to be 49%. Take that 1 minus 0.51. And we can just go ahead and multiply those together by doing this green up here. So probability of getting a boy is 0.51 multiplied times the probability of a girl 0.49. That's 0.2499. Any problems? Any problems? Done. Let me see, we got this last one. Hold on. Yep, last one. Thought so. Okay. So how much do we need to save? Anybody holding on to the red? All right, last one, y'all. We can make it. We can make it. All right. So toss a fair coin 3 times. A fair coin is equally likely to land up either side when tossed. So that's what we're talking about when we say fair coin. What is the probability that all 3 tosses are tails? All right. Anybody holding on to the green? So once again, just like the probability of getting a boy versus a girl, these events getting tails versus head are independent of each other. The probability of landing tails does not affect the next one landing tails or the next one landing heads. The probability of landing tails is 50%. Probability of landing heads will also be 50%. So we want to know the probability of landing tails 3 times in a row. We talked about the probability of getting tails before. I was just walking through it. You know, we have our 2 options down bottom. That's the number of our sample space. Tails just one option in our event. So that's 1/2. So that's how we got that. And like I said, I was just going through that again. So everybody written in black. Don't want to go up too far. So if you're talking about the probability of landing tails 3 times, we're going to do 1/2 times 1/2 times 1/2. That'll give us 1/8. All right. And the other one, what about 2 heads and 1 tail? Everybody holding on to that purple? It's going to give us the same thing, 2 heads and 1 tail. Remember, just 50% for heads, 50% for tails. So it's just still 1/2 times 1/2 times 1/2, which is 1/8. All right. Are we good? Everybody got it? See some heads shaking yes. All right. Some of this stuff, some questions may not show up until you try it out on your own, and I get it. We made it, y'all. We made it. So I think that's it. Yeah, so 5-4 is next class. 5-4 is really more writing. Just no, not really much calculation. That's just like one of those writing sections where, so that 5-4 won't be much next class. So that's it for today. Next class we'll start at 5-4, probably do at least 6-1, something like that. We'll see. But any questions, concerns, comments before we close out? Close out. Everybody good, everybody straight. All right. So if you guys are good, I am good. I will see you on next class, which is next week. So y'all have a good week. All right. Y'all take care.
Alrighty.
Have a
you
good
too.
week.
Take care. Thank you.
You do
Thank
the same.
you.
Have a great weekend, Professor.
Thanks. You do the same. Appreciate it.
Stay safe.
You do the same. Take care.
Mhm.